In this lecture, we will derive the equations for a sink potential. For sink potential, you're considering that all the flow is parallel to the x-axis and is originated, and it's originated and located at the origin. So by sink, we are saying all the flow is actually going inside, uh, going inwards, and the flow rate is given by Q. This is the strength of your sink, is minus because it's going in, R squared, UR, R. Okay? We want to find what are the components of UR, U theta, the stream function, stagnation point, and actually just say the whole thing, how it works. Okay, so as we begin our problem, the first thing that we have to keep in mind that regardless if I'm finding my flow, right, my total flow would be the flow because of my stream plus my flow, my potential, sorry, my potential to my sink. This is not stream, this is flow. Our stream flow is all the same, right? If I'm finding my potential, my stream function, that would be flow plus stream function plus sink, right? So this is what we are really trying to do. So let's start the problem one step at a time and see what goes on. So the first thing we know in the problem is we know that Q bar is equal to rho times the double integral of V dot N ds over S, right? We know that the velocity V will be minus UR ER. Why? Because you can know it's a sink. There's only radial component. There's no theta component in the problem. Okay, so then your N would be nothing else than ER. Okay, and your big R is nothing else than RER. So then you know that, so if I do this integration, you can show that your integration leads you to the following. And also, so when I do this, I find that this is equal to minus URR 4 pi R squared. Okay. Then from here, we know that your UR of R is equal to partial of this respect to big R is going to equal to minus 4 pi R squared, right? This comes from here. And then if I integrate this respect to R once, you can see that your potential flow then is equal to Q 4 pi R plus a constant. Okay? So now we keep moving on, and we can see that your UR in general is equal to R squared sine of theta, partial of psi respect to theta. That would be minus. So we found that this was equal to this. Okay? UR is equal to this. That comes from solving this equation. So if I, from here, so then from here, I can solve for psi of theta. Okay, would be minus sine of theta, 4 times pi. Okay, so then I integrate once, and I find this is equal to Q 4 pi cosine of theta plus a constant. Okay, So now the next thing we have to know from the problem is what is the cosine of theta? Cosine of theta, we have done this already, is nothing else than um, x over r. We did that previously. And we know that sine of theta is equal to r over this, right? Then your big R, just know there's nothing else than your small r plus x squared. So from here, your phi would be q 4 pi r plus cosine of theta, or a constant. Psi will be q times x 4 pi r plus a constant. Okay, and this comes from, this was cosine of theta. Cosine of theta is x over r, so that's where these terms comes from. Okay, so now we move forward, and then for the flow, that was for the sink. Okay, so this is sink. Now for the flow, we know that u of x is equal to u infinite. Note that everything is coming in one direction, so we are assuming that there is no radial components in the problem. So in this problem, then you have ur is going to equal to partial of phi respect to r. This is small r. So from here, you can see that this is the same as minus r partial of psi respect to x, big R, sorry. Then u of x is equal to partial of phi respect to x. It's also equal to 1 over r partial of psi respect to r. So if I take these equations now and I take derivative respect to r, and this one I take respect to x, this one r, this one x, okay, then I can make these equalities and we can find the constants. And just working our way through this, so partial of phi respect to x is given to u infinite. So in other words, u infinite phi is equal to u infinite x plus f1r. Then partial of phi respect to r is equal to 0. That will give you phi to x. So from here, you can see that your flow is nothing else than u infinite x plus a constant. And note that your x is equal to r cosine of theta. This is x, right? So we can say this is the function I'm looking for. Here, this I don't have it, so I make this equal to 0 by comparing both equations. So then from here, your equation then basically becomes u infinite r cosine of theta. Okay, this is flow. Okay, so we found the flow. Just continue. So now we know that 1 over r partial of psi respect to r is going to give you u of x is equal to this, u infinite. That's going to give you partial of phi respect to r will give you u infinite r. Then from here, you find that psi is equal to u infinite We have to go back here. This is small r. This is for the flow. So flow doesn't work with the big R, it just works with the R. So make sure we correct this. And the same thing here. This is small r. Okay, this is small r. So this is correct. Okay, so this one is correct. Then you come here. This is small r, small r, small r, and small r. Okay, then this will give you the over this plus f1 of x. Then you also know that 1 over r, this is u of r. Okay, partial psi of x has to be 0. So from here, you see that you get psi is equal to f1 of r plus 1 of r. So you can say this is this. There's nothing with this, so I'm just going to put plus 0. So in other words, my function that I'm looking for is u infinite r squared over 2. And then phi is psi, and then knowing that r is nothing else r sine of theta, then u infinite r squared sine of theta squared divided by 2. That's your psi. Okay, so now we put it all together. This is flow. Okay. So combining all flows, we know that this is equal to 0. We also know that this for the sink has to be 0. We also know this for the flow has to be 0. So then from here, if I add these two up, you can show that this is equal to nothing else than adding each one of these together, sink plus flow has to be 0. Then from here, phi is equal to sink plus flow. Okay, so I can add them all together. So if I do that, you find that the equation that you get is the following. You see that your psi is going to equal to u infinite r cosine of theta plus q over 4 pi r. Okay, and if you wanted your velocity, then your velocity r is nothing else than phi of your big R, and that gives you u infinite cosine of theta minus q 4 pi r squared. Okay, if you wanted to know what is your radial velocity, that this is your radial velocity, your velocity in theta, that was 1 over r partial of phi respect to theta. That would give you minus u infinite sine of theta, and then you don't have any other components. Okay, and so phi is actually equal to 0 because there's no phi there. Okay, so in the similar fashion, we could go ahead and find the functions for your streamline, and your streamline functions. It's the same idea, right? So you have to apply the Laplace equation, still has to apply. So when we know that this is sink, this is 0, the Laplace for the flow itself has to be 0. And I can add these two up, right? And I find that psi of this is equal to psi of psi sink plus psi flow is equal to 0. And then from here, you find that your psi is equal to psi flow plus psi sinc. In other words, is going to equal to u infinite r squared sine of theta squared over 2 plus q over 4 pi cosine of theta. Okay, so this is what we have as psi. So now if you want to find and remember there's a constant here. So if you wanted to find the constant, what you would do is you would say what happens when theta is equal to 0 has to be 0. I know my psi has to be 0 because that's my streamline. So if I did that and I took this equation, I put a 0 there, it goes away. 0 becomes 1 is equal to the constant I'm looking for. So then 0 becomes 0 plus q over 4 pi plus the constant I'm looking for. And then from here, this constant will be minus q4 over pi. So in other words, your total psi, your stream function, will be u infinite r squared sine squared plus 4 pi cosine of theta minus 1. And if you wanted to express the whole expression only in terms of cosine, you can do that by using trigonometric functions. So now this becomes cosine squared plus q 4 pi cosine theta. Then this becomes plus 1/2 u infinite squared minus q over 4 pi. Okay, so this is a very convenient equation because it helps you to find when pi is psi is equal to 0, right? Put this 0 and you can solve for your theta, right? Cosine of theta, solve this angle and then find your theta. So that's another way that we can do this problem. Okay, so we found this. So to complete our problem, we need to give the full expression, the full analysis, and we need to find the stagnation points. Okay, the stagnation points will be the location where UR is equal to 0. And that happens when for theta equal to 0. So let's see. So you know that your UR was given by u infinite cosine of theta minus q4 pi r squared. When you put theta equal to 0 there, you find that what you get is u infinite. Let's put it down here. So I find u infinite cosine of theta minus 4 pi r. This is cosine of theta is 1. This is all equal to 0. So from here, I can solve for r as stagnation point. And you find that your r stagnation is, there's a square here. So r stagnation would be u infinite 4 pi r, we can call it s, q. So rs is equal to q 4 pi v infinite, u infinite. Okay. Sometimes I use v, sometimes I use u. U and v are the same. I exchange these all the time. Okay. So that's the stagnation point. So if you want to know what is the value of the flow when your radius is actually at the body of your radius when your theta is equal to pi. So here, you know your psi has to be 0. Theta is equal to 0 has to be 0. Okay. There you go. So In the body of your surface, does not matter what you do, this has to be 0 on the body. Okay, this is by definition. And we know that, right? On the body of your surface has to be that. So we know that this has to be 0. So if I take my equation now and I replace all these values, u infinite, RT, call it t at that point, sine squared of pi over 2 plus q over 4 pi cosine of pi over 2 minus 1. And I know this has to be 0. And I solve for RT. You can show that your RT will have the following value. Square root of 2 and q 4 pi v infinite. So if you compare with this, I have the same expression. So I could say this is the same as square root of 2 rs. You can see that the behavior is very similar to the behavior of a source. Now we need to know what happens at infinity. So at infinity, your theta is equal to pi. Okay, so we know that r is equal to r cosine of theta. So we know that your psi is equal to 1/2 u infinite, sine, r squared sine of pi theta plus q over 4 pi cosine of theta minus 1. So at pi, this becomes pi, this becomes pi, right? That is streamlined. So you end up with the following expression. So you end up with 1/2. 0 is going to equal to u infinite rl squared minus q 4 pi 2 equal to 0. So from here you find that your RL is equal to 4 times Q, 4 times pi, V. In other words, RL is equal to 2 times RS. Okay, that's the maximum radius of your problem. So if we want to summarize exactly how everything looks, this is how your body actually is going to react at the infinite. You can see you're going to have, this is your maximum radius. That's going to be generated, kind of stays constant, and then it becomes smaller. And the value right here, this radius is equal to square root of 2 rs. From this location from your sink to the point P, where your stagnation point is, that point will be Rs and is given by this equation. So this kind of summarizes how your flow looks like. Remember, you have the X here, and then you will have a Z going in this direction, if you would, right? That's the Z direction. So this summarizes this the derivations for this sink. They're very similar, as you can see, but they're flipped on the other side now, right? Because they all go inside, so we flip the equations. Okay, this concludes the discussion on sink potential flow.